Awesome. So my name is Jeffrey Hood. I'm a researcher and modeler at Metro, focusing on land use modeling. And I guess it's been almost a year now, we have been working on development of implementation of the UrbanSim cloud-based land use modeling platform for the Portland Metro region. And I think that the title of in the agenda was Metro's new land use model. I might say it's like Metro's new land use modeling platform. We're still in kind of the late stages of development. And so I'm going to kind of give an overview of the platform, the pieces that we're still working on, and then talk about our plan to apply this to the distributed forecast of population and employment, hopefully to be adopted this year. And possibly, if time permitting, give you a tour of the UrbanSim cloud platform. So let me just step back for a second. So no, it's fine. Here we go. So the UrbanSim, focusing on the middle of the slide in the center column here. The UrbanSim platform that we have, it takes control totals for the annual change in households by income and employment by industry. And then it has some household models where the households choose to relocate or migrate into the region, and then they choose a location within the region. And so that's the household relocation and location choice models. Then, in order to return a number of residential units in the region to a structural vacancy rate, the residential development location choice model takes the need for new housing units and allocates them to different locations in the region based on a bunch of factors. And then also jobs relocate and choose new locations in the region. And then finally, there's a real estate price equilibration, which adjusts the real estate prices based on the balance of supply and demand in different areas of the region. And then those prices get fed back up to the top. Although it doesn't, I put this arrow going all the way up to the annual household change in households, but that doesn't actually have that macroeconomic integration. So the arrow should only go from the real estate price equilibration to the household relocation and location choice model, and not the change in the total number of households. So on the left side of this slide, we have all of the inputs to UrbanSim. And then on the right-hand side, we have the big output of UrbanSim, which is households by income and employment by industry by block, which then is going to be fed into our transportation models, which finally feed back another input, which is the network level of service travel times from the transportation model. So on this slide, there's a whole bunch of color coding and variety of things, but basically the solid blocks are pieces that are complete, that we completed in the last year in our urban growth report. Regional economic model takes a whole bunch of macroeconomic and regional factors, demographic factors, births, deaths, etc. And for the entire metropolitan statistical area, forecasts the number of households by size, income, and the age of head by year, and also the employment in some kind of medium industry aggregations. So the boxes that are kind of dashed and shaded a little bit are the pieces that we're still working on here. So, and the orange slides, the orange boxes, they kind of live in our finance and regulatory services because they involve, labor and industries and economic factors that are really outside of construction, land development, transportation, real estate, that type of analysis, which lives in our planning department currently. And so, but one thing that we need to do in order to get to a final UrbanSim implementation that we can apply to the distributed forecast is to remove some ex-urban counties that are in the metropolitan statistical area, Yamhill, Columbia, and Skamania counties, because all those are in the MSA. They're not in our 4-county transportation model, and so we can't integrate them with the network level of service matrices. So once we have those 4-county control totals, then those will inform UrbanSim for the annual change in households by income and employment by industry. Then there's another input which is in the wheelhouse of the planning department, which is the residential development capacity and profitability. So this is an estimate which is almost complete by our urban growth report process that we completed last year. But what that is at a block level. I mean, really, it comes from the parcel level. So it's kind of like UrbanSim is still kind of a hybrid block level, parcel level model. So the development, that's the number of housing units that could possibly be built, and also the profitability, which could be expected from developers, building new housing units in different locations in the region. And then finally, we need the employment capacity to get the job relocation and location choice model, so that jobs in different industries are going to the locations where they're most likely to locate. So continuing with the overview, these are the household models. So you have the new household population, and then you have the relocation model, which is the current population. Do they relocate? And then they actually choose a tenure as well. And then the households the new households and the households that are relocating with the region choose a new location. And then that decision is constrained by the residential units that are available. The residential unit models, or the development model, it looks at the long-term structural vacancy rate and kind of puts into the region a new queue of residential units that need to be allocated to locations by builders. And the demolition model, which we may actually not use, since it's apparently, I don't think it's going to be necessary to get this done, but that models the current decision of people to demolish units that can then be developed to a higher capacity. And then those residential units are allocated to locations by the residential development project location choice model, and constrained by the residential capacity and influenced by the profitability and other factors like access to jobs and prices and things. And then finally, the employment models. There's new employment coming in because of new firm decisions, and then also relocation model. Jobs relocate within the region, and then those are allocated by the employment location choice model and constrained by the employment capacity. The new cloud, one of the great features of the new cloud-based UrbanSim model, which seems like very new, and it's very exciting, and so far seems well implemented, and very proud of and very excited about, is the new machine learning calibration. So all of these models now can be jointly and longitudinally calibrated using the change in development and change in locations of jobs and households over the calibration period from 2010 to 2020. So they're all jointly and longitudinally calibrated for all of these models all at once over time using an differentiation framework where the the derivative or the change in outputs relative to the change in coefficients in the model is calculated on the fly according to the combination of all these models together, using a machine learning code. And I'll hopefully have time to show you a little bit about how that works when we do the tour. Oh, finally, there was the price adjustment model, which I didn't get into yet. So the price adjustment model looks at the supply and demand, and it if in locations where the demand is very near the supply, the prices will go down, and where the places where there's excess supply, there's a higher vacancy rate than the structural vacancy rate, then those prices will tend to go down. I'm not actually sure right now how this is used in the employment models, but I know that this I think is what is describing the residential models. So finally, I want to talk about this, our proposed schedule to complete the distributed forecast this year. So the draft urban growth report was completed around last July, and then it was adopted by the council, and there was a decision to expand the urban growth boundary in Washington County in west of the city of Sherwood. And that was done in December 2024. And then following kind of the same cadence, we're looking to complete a draft distributed forecast by July of 2024, which will then be adopted for the 3-county area in December of 2025. Following that, in the next year, we'll do reconciliation with Clark County, Washington, and also we have a new expansion to our metropolitan planning area, the federally designated MPO planning area in northern Marion County in the cities of Aurora and Hubbard and Woodburn. And so we'll need to add that into the model following the council adoption of the 3-county area. And then that will all be used in our next RTP, which is due in 2028. So that's kind of the overview of the platform. And now I will kind of show you what it looks like on the web here. So this is the UrbanSim scenario modeler. The metros look at that, and so we can create a new project. I'll call it the OMSE demo, and I select the Portland Area Metropolitan Service District, and I say we want to do regional scenario modeling. So you open this up, you get the data library, which has a whole bunch of layers here. So we can look at building footprints. You can add a bunch of layers at the same time. And, it's just kind of your standard GIS viewer stuff. Might be taking a minute to load. So, there we go. Just got to zoom in, which has data about the height of buildings and the building footprints to help us get the floor area ratios of desired. And I'm going to dig right into the kind of the secret sauce of UrbanSim, which is this automatic differentiation calibration framework I was describing. I'm realizing I was looking at that and thinking it was 4 minutes and 20 seconds a while ago. Now I'm realizing it's 4 hours and 20 minutes. So what time is it right now? I've been talking for 16 minutes. Okay, great. So right now we're working with model version 1.0.3, and to run a new calibration, these settings are kind of, we just leave them the same because they're in the gradient descent algorithm, which is used for parameter search, and unless the calibration breaks, we don't really need to to change them. And so the way that we specify variables is with this variable definitions file. And I've downloaded one of those, so I'll just go ahead to that. So there's a whole bunch of basic data in the UrbanSim model, the residential units for 2010 and 2020, et cetera. And then there's this kind of shorthand code to define new variables for the model if we want to test them in calibration. So there's a lot of interesting functions that come in here from a machine learning library that make sure that the surface for gradient descent and searching for the new parameters doesn't blow up. So there's a lot, safe divisions and these, I forget what JAX stands for, but it's a NumPy library for machine learning. So, it calculates the renter's vacancy rate is this function based on the division of renters to units, but there's a safe divide in there to take into account that we don't want this automatic differentiation framework to blow up. And so there's all this plumbing in the background that then create all of these functions are all differentiable natively, automatically through the platform. So I don't need to specify what the gradient is for the loss function, which the model is searching for the optimal solution to calibrate all these parameters. That all happens behind the scenes using the UrbanSim's new secret sauce. So after we have the variable definitions, then we can create a model specification for the parameter search. So, for example, here in the demolition model, for units that are owned, there's a logit function, a discrete choice model based on multinomial logit model, just choosing, I guess it's binomial logit, whether to demolish the building or not. And that by putting these terms in there, the function will now have an intercept. It'll have the logarithm of the age of the building, the job access, the price, the number of units, and the proportion of persons in the block who have a low income. And I guess this is all actually at the block level. So all the parcel level data that we feed into the model all gets aggregated into the block, and then the model is deciding how many units to demolish in the block, which is obviously usually very close to 0 in 1 year. So when we do the calibration, we feed it this arbitrarily small number that's not 0, but so that the gradient descent is able to begin. And then when the calibration finishes, we get the optimal specification based on the solution of the large, many parameter combination of multinomial logit models. So this happens to say that some of this is a great example of why we still need to work on this a lot, I'd say, because a lot of these variables are correlated together. So the built age, this is saying that, if I'm understanding correctly, the more likely, the older a building is, the more likely it is to be demolished if it's owned. The less likely it is to be demolished if it's owned, which to me is not in concordance with expectations and reality. And so this is, I'd say,
log, right?
What?
Well, it's a log, right? So that just means that the built age is less than 1. Yeah.
No, so this is the coefficient that's being applied to the logarithm of the built age, right?
Yeah, I got you. Okay.
So I think what's probably happening here is that you have all these variables that are correlated together, and the machine learning, it's probably overfitted right now, and we need to take some of those out. I'd say a downside of this machine learning calibration method is that we don't get all the familiar statistics. Like, we don't know what the standard error of this built age coefficient is. So we have to do a lot of diagnostics outside the model to look at, why might this coefficient be reversed and need correction. And that's probably one of my dreams for long-term development for UrbanSim for this framework, is that they can look into creating some sort of, not only to do the gradient descent and calculate the minimum of the loss function, but also to look at the curvature of the loss function, so we can understand how rapidly these coefficients change. I mean, the loss function changes as we move away from these coefficients, and that could help us determine whether we're at some local minimum that's not actually the best solution. Okay, so that's the calibration interface, and I'm starting to go into the questions time, so I'll just briefly mention that once you do the calibration, then you just, after that, it's really just hit and go, I suppose. So I create a new scenario and input the control totals, which is the number of households and employment by income and age. And then, so I create a new year, 2030, and input this. Maybe it's not 1 million, maybe it's 1.2 million, et cetera. And then that's really the only thing you need to change. And then you just hit the button, and you get a lot of you get all of the there's maps and stuff like that. But another thing I did want to show you was the calibration that we kind of has been selected to be delivered to us. There's all these diagnostics down here looking at. So this is for households. The change in households for over 2010 to 2020 has a 85.85 correlation, and you can look at the housing units, which is very tight. So the development is definitely being directed to the proper place. Employment is reasonably tight as well. These things start to break down right now around the rents. The rents are kind of the weak point right now, but for the distributed forecast process, we're not really concerned about rents and prices, but the prices do a little bit better than the rents right now. So with that, I will stop talking and open it up to questions. Thank you.